And yeah, so that being said, I will let Lydia take it away for chapter 1 here. And yeah, and then we'll move on. So you're more than welcome to start whenever you want, Lydia.
All right, thanks. Hey guys, I'm going to start with chapter 1 and then I'm going to let Anne-Marie take it back over. So we start with populations and samples here. So basically this is all about gathering information, and we basically want to gather information so that we can make inferences about populations. But since it's very difficult to gather information from populations, we gather information from smaller groups of people, which is called a sample. So we make inferences about the population through samples, and the measurements and how we measure populations are called parameters here. And we measure samples through statistics such as X bar as the mean, P has the proportion, and such as parameters such as mu for the mean and P for the proportion as shown there as well. So for variance, we also see, oh, thanks. For variance, we see S squared for sample statistic and sigma squared for parameter, which is similar to standard deviation, except we don't square those. So we describe variables there's two variables that we use. One is the explanatory variable, the other is the response. In science classes, you may have seen independent and dependent variables. Those are similar to explanatory and response. They're the same thing. So explanatory explains differences in the response variable, the outcome variable. So such as, for an example, do the number of credits taken affect your GPA? The number of credits you would take are the explanatory variable because they explain, or you can measure the GPA as the response. So more on independence and dependence. Independence is unrelated. The variables are unrelated. The randomized comparative experiment measures groups independently, and the cases are randomly assigned to different conditions of an experiment, so it makes it more reliable in the end. Also, they don't affect each other, whereas for dependence, they do affect each other. And there's a paired and matched pairs experiment, and the subjects are the same in both groups for those experiments.
Yay! Okay, yay. Thank you so much, Lydia. What a beautiful rendition of chapter 1. We appreciate it very much, so thank you for that. So yeah, hopefully that, was a good start for you guys to try to, just kind of understand, where we came from the beginning of the semester. We're already in week like 7 or something. Like, I don't even. It's flying by, but now we're gonna. So I kind of grouped chapters 2 and 3 together, and also 5 and 6 for hypothesis testing. It's because it made more sense because they're both the same topic, but remember we did like part 1 and 2. So like I said, I just kind of grouped them together. So yeah, and you guys are more than welcome to ask once again like clarifying questions as we go through. Just like save like specific questions for the end, but like definitely if something like doesn't make sense, please ask me, definitely, so that we can get that cleared up. Okay, so we're talking about variables. So Lydia talked about us having explanatory and response variables, but we also have categorical and quantitative variables when we're talking about basically like how the variables are categorized, like how are they, do they have values attached to them, or are they just labels? So categorical variables are going to be those that have names or labels. I always think of these things that basically you can't put a value to them, so theoretically. So things like colors, flavors. You guys, if you've been in my reviews, I use these same examples because they make sense. But there's plenty of them. You can, and if those don't make sense to you, you can later Google categorical variable examples. Like it's just anything that you can't assign like an actual like value of, like you can't say that red is worth 7. That doesn't make sense. That's categorical variables. Inconsistent differences between the groups is saying the same thing, that you can't have any sort of like number attached to them and error value. And then we do have two different types of categorical variables. We do have nominal and ordinal. Nominals are just categorical variables that have no meaningful order. So those are the things like brands of something or types of flooring. Not really sure why I said that one, but that's an example. So you can't, you know, laminate doesn't come before hardwood, or, you know, so that's a nominal categorical variable there. So then we also have ordinal, which they are going to have some sort of order to them. So those are going to be categorical variables, so they don't have a value to them, but they do have some sort of order. So any type of class ranking, anything that's like, or like in the Olympics, like, you know, bronze, silver, gold medals, if, you know, that would be considered ordinal, because, you know, bronze is always before gold, that kind of thing. And then we have quantitative. Quantitative, just they always have values attached to them. They have to have a meaningful order, obviously, because numbers always have a meaningful order. Discrete are going to be ones that take on a set number of values, basically anything that you can't like split apart. So people, like dogs, that kind of thing, animals in general, things that you can't have, you know, different like parts to. And then continuous will just be ones that can basically take on any value between the minimum and the maximum. So these are things like different weights. I think of these, I mean, quantitative variables are also called measurement variables, but I think continuous ones are like true measurement variables, because any type of measurement such as like, you know, weights, heights, any like inches, that kind of thing, they're always going to be continuous because you can have any amount of those. So, okay. Okay, so we have quantitative data displays. So basically, with quantitative data displays, this is these are just examples of different types of distributions or displays that you can use to display quantitative data. So remember, these are going to be different variables that have a value attached to them. So these are different ones that you can use. So all these can only be used for quantitative data displays. They can't be used for categorical or any of that. So we have our box plot over here. If you guys recall, this is good for talking about our quartiles. We can see the middle 50% of the data really easily. Side-by-side box plots, if you remember, they're good for comparing things in terms of that and minimum, maximum, that kind of thing. Histograms, remember, the bars touch in those because for quantitative they can share a number, when in categorical they can't really share a category per se because there's inconsistent spacing between the groups. But in a histogram the bars do touch because, you know, the number line, those numbers are continuous there in that case. And then we have a dot plot over here, which is basically a histogram with dots. So it's showing a distribution, but each value is represented by a dot. Histogram, this is basically like the entire grouping of the values, so each individual one isn't placed. And scatter plots, if we talk about those a little bit more, remember we have 4 different ways that we discuss scatter plots. So once again, this is talking about categorical or quantitative variables, so they have some sort of value attached to them. And like Lydia told us, we have response variables and explanatory variables. So explanatory is always going to be on the x-axis. It's explaining whatever is on our y-axis here. So our explanatory variable is our independent variable. So as you move across this number line down at on the x-axis, you have a change in the response variable. So whatever happens down here is going to influence what happens on this y-axis with the response variable. So this response variable is dependent upon our explanatory variable. And we just discuss it in terms of direction, form, strength, and outliers. So basically, our direction is just positive or negative. This can get a little, SOS. This can get a little confusing. So I just want to review really quick because some people get a little tripped up with this. So when you're reading to try to figure out if it's positive or negative, you always want to read left to right. So if I were to draw a scatter plot that looked like this, if I'm looking from left to right, this is going down. So this is going to be negative. And then likewise, if I were to draw one that's going like this, even if it's not in a straight line, and then from left to right, it's going up. So this is going to be positive. So always remember to read it from left to right in this case. that's where a lot of people get tricked up. But as long as you read it from left to right, you should be good to go with your direction. Form is just talking about if it's linear or not linear. Does it look like a line or not? And so that's where you get your form. Strength is just saying basically how close are these dots together? Are they strongly correlated? We think there's some sort of relationship going on or not? And that'll just talk about our strength. So if we think there's a high or a close relationship between the two, it's probably going to be more moderate or strong. And then if we don't, it'll probably be more on the weak side. And then we have outliers, which would be, any type of like variable or like point that we got that's like totally out of the norm, that's like definitely out of the way of like our normal, I don't know what I just drew there, but our normal distribution and the different points that we got, something that's like totally out of the ordinary. So that's an outlier. All right, so let's keep talking about. Okay, so then specifically talking about outliers, remember we do, if we want to objectively look at outliers, we can use the IQR method in terms of a box plot. So if we have our box plot here, remember our IQR is going to be our area in here. So it's from our Q1 to our Q3. So it's this area here. And then basically the whole point of the IQR method is to create that area around Q1 and Q3, basically to say that if it surpasses this area, then we're going to consider it an outlier. It's basically more objective than just looking at our, like the data and being like, yeah, that looks like kind of far away, that must be an outlier. This is basically allowing us to say, okay, we definitely understand that this is an outlier because the IQR method shows us that it's surpassing this area around Q1 and Q3, and if it does pass that area, we can consider it an outlier in that case. So that's the IQR method. Oh, and so basically, and the way to find it, you just find your IQR, which remember is Q1 or Q3 minus Q1, and then you just multiply it by 1.5. So if you think about it, it's basically going out 1.5 standard deviations per se. So it's saying that anything past that is going to be an outlier, which kind of makes sense. If something's more than 1.5 spots out from your middle 50% of your data, that's going to be an outlier, and it's pretty far out. So far out, dude. Alrighty. Okay, so this is just a good visual to remember basically how we describe the shape of quantitative variables. So we're still talking about quantitative in this case, just remember. So we're still talking about quantitative variables here, and these are just different shapes. Definitely, kind of understand to make sure, where these are coming from. So symmetrical is just the idea that our mean is equal to our median, which is equal to our mode. So everything's in the middle, everything's the same. So it's symmetrical, it's the same on both sides. So that's pretty self-explanatory. It's a mirror image. And then we have skewed to the left, which means that our values on the left side are more spread out than those on the right. So I think it is important to remember these three things down here, that our mean is less than our median, which is less than our mode. Kind of helps you, understand this kind of curve. So if you think about it, our mode is going to be our where the highest point in our graph is, because remember, our mode is the most commonly occurring number. So this is going to be the highest point in our graph, which is right here. So that's why our mode is all the way to the right here on a left skewed data set, and then on a right skewed distribution, we will have the mode down here, because remember, our values are more spread out on whichever way it's skewed. So that means our average will make more sense. Our average is going to be in the direction of where that skew is, because that's where most of the data is going to be spread out down there. So as you can see, skewed to the right, the mean is closest to the skewed side. Skewed to the left, we do have the mean closest here to the left side. So it's just different ways to view the distributions of quantitative variables. Oop, put a little dot there. Okay. Let's see. Okay, 5-number summary. So this is basically how we talk about, like, this is just like summarizing our data in 5 different numbers, obviously, but they're representing kind of like an equal continuum, like along a number line. So we have our minimum and our maximum, and then all the stuff in between. So if we were to actually look at this, like on a visual, 5-number summary is really just represented by a box plot. And so we do have our minimum at the bottom here, and then our maximum. And then, we do have our Q1, and you guys probably have seen me draw this a million times, Q2 and Q3. Definitely draw it yourself so you understand, where these things come from. And remember that Q1 is in our 25th percentile, Q2 is our 50th because this is our median, and then we do have Q3 in our 75th percentile. So remember that each of these is representing 25% of our data. So you see here for Q1, 25% of the data lies at or below Q1. So that's why we consider it the 25th percentile. And same here with Q2, we have 50% of our data. So that's why 50 is, same thing with 75. And the max obviously technically is the 100th percentile because 100% of the data lies below, at or below the maximum. So that's a 5-number summary. Our range is just going to be obviously our maximum from our minimum. And we talked about the IQR. This is going to be our area within here. So it's the same thing as a range, except it's within the quartiles. That's why it's called the inner quartile range. That's where that comes from. So, okay. Okay, the empirical rule. Love it. It's my favorite. So the empirical rule is basically just showing you the percent of the data, no matter what type of distribution you have, as long as it's normally distributed. You can talk about the percent of your data which is within plus or minus 1 standard deviation. So no matter what numbers you have going down here, you can have, as long as it's plus or minus 1 standard deviation on that curve, it's going to be 68% of the data. So if I had something like a curve that looked like this, kind of looks like a spaceship. So let's say that I have my mean of 100, and then my standard deviation is 10. Okay? So if I draw 100 here, and then I'm looking for the area in between these two numbers. So I'm looking for this area in here. According to the empirical rule, as long as this is normally distributed, I can assume that plus or minus 1 standard deviation is going to be 68% of my data. So I can conclude that this is 68% of my data. You can't really see, but because it's within plus or minus 1 standard deviation, because you saw we went down 1 standard deviation, so minus 10 to get 90, plus 1 standard deviation to get 110. So I can conclude that this is 68% of the data. So same idea for the rest of them, but it just translates basically to any situation. This is just shown basically if we have a mean of 0 and then a standard deviation on this specific curve, but it can be translated to any situation there. All right. Okay, so now we're going to talk about categorical data displays. So this will be basically, everything we just talked about was quantitative. So this will be for categorical data. So remember the type of data that is labels. So we have bar graphs and two-way tables. So the different bar graphs I have here are basically just if you're talking about one variable or two. So we have our one variable bar graph, which is bar graph, bar chart. You'll hear it both ways, where you are just representing your variables, the different categories on your x-axis, and then you will have your frequency of each variable on your y-axis here. And remember, the bars don't touch in categorical variable or categorical data displays for a bar graph. So yeah, bars don't touch here. They do touch in histograms for quantitative data, but not in categorical. And then the other two that I just have represent here in segmented or stacked or side by side, it's just if you want to do represent two variables just in different ways. So obviously you just stack them here for a stack bar chart, not here you just put them side by side so you can compare them. So it's just another visual way to compare the frequency of a categorical variable in this case. And a two-way table is a good way to represent the relationship between two variables too. So we'll have, football and basketball in this case, and then you'll also have, you can football, basketball, baseball, whatever, and then males and females. So you have sport and you have gender. So those are your two variables, and then you're able to kind of see the different connections between them. So, 12 females like football when 16 like basketball. You know, you're able to find that in a two-way table by just finding the intersection between each of them. And then your totals are given here. You can also give the totals over here for like total number of males and females that you had too. Okay. Okay, so now if we want to like mix the two up, because we're going crazy, we can do a quantitative and a categorical variable together. So in this case, this is stuff that we've seen before, you know, like, so it kind of, you've seen like the box plots by themselves, histograms by themselves, and dot plots by themselves to just be for quantitative variables. But you see here, if we want to add in a categorical variable, we can basically just put it over here. So here we're stacking our histograms to have one categorical variable here, one here. Same thing with dot plot. It's the same thing. These are always very similar. Dot plots just show each different like observation as a dot. And then here with side-by-side box plots, we talked about this a little bit. So you do have your quantitative data here with your age, but then we do have different categorical data here with gender down here, so an actor and an actress. And that gives you the chance to, you know, compare your maximums and your minimums, you know, and your medians and that kind of thing. So, so yeah, this is good to compare your quantitative and categorical variables together. Or like, you know, comparing your quantitative variables in terms of categorical or vice versa. So, okay, risk and odds. Yes, super fun. So risk and odds are very similar in the fact that they are both describing the likelihood of an event, but you do interpret them differently because your denominator is different in these different equations. So your risk is just talking about basically the same thing as a probability. The probability that's going to occur, so the risk of it occurring. Because if you hear, you know, the risk of this happening is, you know, this percent, it's saying like the risk that it'll happen. What is the probability that this is going to happen? So that's why our denominator here is our total number of outcomes. So we have the number with the outcome, and then we do divide that by the total number of outcomes. And then for odds, we do change that denominator to number without the outcome because we're trying to compare it happening versus not happening. So basically that's why we have like happening as our numerator and then not happening as our denominator here. So that's basically where we get that from. And then also if you are given the risk, you can do your odds equation like this, because if you think about your risk, remember, is the probability of it happening. So this is technically like it happening. And then our denominator is going to be that's not happening, so that's obviously going to be 1, our total minus the risk of it happening. So this would be not happening. So translates to the same thing. It just depends on what information you are given there. So very similar, but definitely just understand the difference between them. Okay, combination of events. We went through this a lot in my video, you know, when we did the actual lesson for this. So if you want more clarification on this, go ahead and watch that video. I don't want to take up too much time on it because there is a lot to these. But just as a quick review of them, we are talking about 2 or more categorical variables, okay? So we want to make sure that we're talking about what is the relationship or the combination, you know, between these categorical variables. So the main thing to keep in mind here, I think, is just, you know, especially like these symbols here, that you have, you know, for your intersection, you have this like upside down U looking thing, and your union, you have a normal looking U thing. Just understanding the difference between these. And like I said in that the video for this actual lesson, we have like more visuals and stuff of these. But you know, intersections, probability of A and B occurring, and then union is going to be probability of A or B occurring, which also includes A and B, because if A or B occurs and A and B occurs, and technically A or B is occurring, they just both are. Complement is everything except for A, so everything except for what you're looking for, so probability of not A. Conditional, this is basically just how you read that, the probability of A given B. So it's saying that B has to happen first before A happens. And then independence is just talking about that the fact that like if they're not related at all, which Lydia told us about earlier. So definitely, that was a good explanation of what independence is, how they don't affect each other. They're not related in any way. So that would be what independence is in that case. Oops. Oh my goodness. Okay, correlation. Basically, this is just similar when we were talking about scatter plots, kind of along the same lines of the fact that we do talk about strength and direction, but correlation is specifically those two together. And there's a linear association that it has to be linear in order for us to talk about correlation. And this is for two quantitative variables. So we're talking about quantitative variables again. And we talk about here the absolute value of R because it's either positive or negative, but the positive is, if you saw one of these numbers, that's saying that it is a positive relationship, a positive direction, while if you saw negative numbers, it's not saying that it's like a negative value because there is no unit associated with R. It's just a number. So if you saw a negative with it, all it means is it's in a negative direction, not that it's a negative value at all. So that's something to keep in mind. And these are just basically like examples of how we would describe these different like correlations. So. Okay, yay, confidence intervals. I'm gonna lose my voice. Oh. Okay, let's do confidence intervals. Okay, so these basically, when we talk about confidence intervals, remember we're talking about that range of the data that we are able to compute given either statistical software, or we can use this equation, the given like equation of point estimate plus or minus our multiplier times our standard error. I've been using 2 often just as an example because we often use a 95% confidence interval. So that multiplier of 2 is something we often use. Our point estimate is always going to be our sample statistic. So remember what Lydia told us was that we wanted to make sure that we're able to differentiate between these types of variables. So our p-hat and our x-bar are going to be sample statistics. So you want to make sure those are the ones that you're plugging into your equation. Your point estimate should be a sample proportion or a sample mean. That'll be your center. You never want to use the population one in this case. You want to use your sample because remember, she also told us about how with our population, it's hard to gather data from that, so that's why we use sample. So we're using the sample statistic as our center of our confidence interval in this case. So you're going to use your sample here, so either p-hat or x-bar if you're talking about proportions or means. And then your multiplier will just be basically in terms of the the empirical rule, so 2 for a 95% confidence interval, which I think I have another slide that talks about this. But remember, plus or minus 2 standard deviations is going to be 95% of our data. So that's where we get that multiplier from. And then our standard error just talks about categorical variables. If we're talking about categorical variables, that's when we're talking about proportions. So that would be with p-hat. And then if we're talking about quantitative, we will be talking about means. So those are correlated. Just keep that in mind. And then just a note that as our sample size increases, then our confidence interval will be more narrow. So in this case, we just want to make sure we understand that aspect that, if we have a larger sample size, then that's better because we have more to go off of. It's going to be more representative of our population. Because if you think about it, the larger the sample size, the more of the population we're actually getting, so the more representative it is. And then we'll get a more narrow confidence interval, which is good because then we're saying that we're this % confident that that the value that we're looking for is within this confidence interval. So the more narrow it is, the less we have to choose from, which is better for us. So that's what a confidence interval is. Okay. So I just explained this. This is where we get that multiplier plus or minus 2. Can't really see this down here. So we have our sample statistic. And then plus or minus, here's our multiplier of 2 for a 95% confidence interval times our standard error. So remember, that's just our general equation for a confidence interval. So that's just explaining the empirical rule and where it comes into play here. Okay, so interpreting a 95% confidence interval or any percent confidence interval, this is how we would interpret it. So after we get our range, so we get that lower bound, higher bound, we finish that equation, we do point estimate plus or minus 2 times the standard error. What you want to do is now interpret that. So you always start off that we are whatever percent confident, whatever interval you did. So in this case, we could say we are 95% confident that the population, so we always have to put that we're always making inferences about the population. So it's always going to be population here. Remember, Lydia told us that we have to be talking, that we use those samples to make inferences about the population. So our interpretation is always going to be about the population, because we don't have to make, be confident that our sample proportion is within there, because we used our sample proportions to find it. So we're trying to be confident about the population. So this is either going to be our proportion or our mean in question, is between the two values that you got. And I showed you down here that, your lower bound, upper bound is what you actually calculated from that equation, or, statistical software. Your sample statistic plus or minus 2 times your standard error. That's going to give you an interval such as this, and that's what you use to interpret it in this way. So that's just like a general sentence that we're able to say at the end when we interpret it. And you will, also include the context of the problem, confident that the population proportion of whatever variable you're looking at. So we have some questions about that in the actual review. So, woo, okay. Okay, bootstrapping, yay. This is not, don't look too far into this. Bootstrapping, all this is talking about when we're taking samples, but then instead of just continually taking samples, we do put the value or the different sample that we just took, we put that back into our original, basically like mix that we're going to be taking out of. So remember, our standard deviation of the bootstrap distribution is our standard error that we're able to conduct that confidence interval out of. So, they're kind of synonymous. Our standard deviation of a bootstrap distribution is our standard error, and that's where we create that confidence interval, but it would be with bootstrapping. So, yeah, that's standard error method. Remember, because with our standard error and our standard deviation, remember, we could only apply the empirical rule if we had an approximately normal curve. So we can only use the standard error method if we have an approximately normal curve. Percentile method can work regardless, because there's always going to be a certain percentile. Like, it doesn't matter how normal or not it is. There's always going to be 100% of the data between the minimum and the maximum. So there's always going to be percentiles in there no matter what. But standard error does have to keep in mind that it has to be normal in order for you to find a accurate standard error in order to use the standard error method in that case. Woo, okay, chapters 5 and 6. So this stuff should be fresh in your mind, guys. For hypothesis testing. So when, like at the beginning, when you're writing your hypothesis, you want to make sure that your null hypothesis always has an equal sign, because our null is saying that there's no change, that basically when we think that there's no change in the population given the samples that we took. Alternative is saying something's going on, there's some sort of change, and depending on the situation, what they're trying to decide, it could be less than, not equal to, or greater than. So our alternative is never going to have an equal sign. Null will always have an equal sign, nothing else. And yeah, our alternative is just saying some sort of change is going on. So that's why when you interpret it, you're interpreting it as we reject or fail to reject the null, because we're trying to decide, do we think there's a change, do we think there's no change, and go from there. Okay, p-value. So remember, our p-value is a probability. So we end up getting this p-value after we do all this statistical analysis, and we have to decide basically what this p-value means. So if our p-value is greater than our alpha level, so remember our alpha level is our significance level, if p-value is greater than that, then we're going to fail to reject that null hypothesis. And if we fail to reject the null, so this is saying that we fail to reject that there's no change, we're not able to conclude that there's a change, we're going to assume that there's no change. We're assuming that the null is still true. Even in general, we do always assume that the null is true no matter what. But if our p-value is greater than alpha, we keep that assumption basically. We assume that there's no change and that the null is still true. But if our p-value is less than alpha, saying that there is like a low probability that basically we got it from random error, then we're going to end up rejecting that null. So we're saying we think there's some sort of change. We're rejecting the fact that there's no change. So we assume that there was no change, but our p-value was less than alpha. So we're going to reject that null and say we think there's some sort of change. And that'll be contextual, dependent on what sort of change was being tested in the hypothesis test for the context of that problem. So yeah, then we just conclude there's a change, and then it's in favor of the alternative, because remember, the alternative is never going to have an equal sign. It will always have some sort of inequality. So we're in favor of that inequality. We're in favor of the change, which is the alternative hypothesis. Okay, so when we do hypothesis testing, we do acknowledge errors that we can make. So our type 1 error is the same thing as our alpha, our significance level, because that's the probability that we reject the null when the null is actually true. We commonly use 5%, 0.05. It can be different. You sometimes see 0.01. Depends on how much percent you're willing to give that you made a mistake, basically. So type 1 error is basically saying that there is a change when there's not a change. So HO being really true is meaning that there's no change, and then your type 1 error would be made if you say that there's a change, but there's not one. And then the type 2 error means we're failing to reject the null when the null is actually false. So you're failing to reject that null. You're saying that there is no change when in reality that null is false. So if the null is false, that means there is some sort of change. So yeah, that's a type 2 error. We say that there's no change when there is a change, and we call that beta. So yeah, alpha is our probability of making a type 1 error. Beta is our probability of making a type 2 error. And then this two-way table down here is basically showing you, depending, you start on the left side there, depending on what decision you made, and then what actually happened in reality. You can see basically if you made a correct decision or if you made an error. And I just showed you to remind you here that alpha is a type 1 error and beta is our type 2 error here. And then power, I think we talked about power Power is going to be basically everything except for the probability of making a type 2 error. So, by definition, it's a probability of rejecting a false null hypothesis. And I understand statistics is a lot of like reading these things and like kind of understand them in your head, saying them different ways. You probably notice I try to say things in like 8 different ways, because sometimes it'll click with different people, the different language you use. But by definition, the power is the probability of rejecting a false null hypothesis. So the probability that we reject, so we say this is wrong, but it's a false null. So if we were to translate that to something a little more easier to think about, it's making a correct claim that there's some sort of change. So remember, a beta is the probability of making a type 2 error. So 1 minus beta will be everything except for the probability of making a type 2 error. So that is going to be making a correct decision. So 1 minus beta is our power, and that's making a correct claim that there's some sort of change going on. So that's basically correctly rejecting our false null hypothesis. So correctly saying that there's some sort of change going on and rejecting that null, which is saying that there's no change. So we're saying we reject the null, we reject that there's no change, and we are claiming that there is a change. And obviously, yeah, just inversely related with probability making a type 2 error, because obviously if your beta goes up, your power is going to go down, and vice versa. So it's pretty self-explanatory. Oh, we are on review questions. How exciting. Okay, so we'll go through some reviews here. If you haven't done this before, basically we will read through these, or I'll read the question, and then go ahead and read the answers, and then type in the chat box what you think your answer is. If you don't know, you can say that too. And after a little bit, we will go over it together as a group. So let's start with this one. So which of the following statements is correct about a parameter and a statistic associated with repeated random samples of the same size from the same proportion or population, excuse me. So go ahead, read through these answers and let me know what you think, and we will go over it together. Okay, good job, guys. Absolutely. So our answer is B in this case. So let's talk about this. So remember, our population is something that's fixed. And remember, population is the measure of it is a parameter. And then I'm sorry, that is not very clean. But so population goes with a parameter, and then our sample, our measurement of that is a statistic. So in terms of this, if we go through A, it says values of a parameter will vary from sample to sample, but that's not true because remember a parameter is a population, the measurement of population, and this is always going to be fixed. So that's not true that they will vary from sample to sample, and also saying that statistic will not, that's also untrue. So A can't be our answer. C says values of both parameter and statistic may vary. Not true. Parameters are fixed, so that's not true. And then D is saying values of parameter will vary. Again, not true. So D is our correct answer because statistics will vary because they are randomized usually. And then, yeah, according to the sample distribution. So that's why B is our answer. So great job, guys. Definitely understand that. All right. And if someone doesn't understand this, please, stop me and we can review it again, obviously. Okay, so number 2, so which of the following variables will we use a bar graph to display it? So it's talking about different types of variables and displays for them. So go ahead, read through these and let me know what you think. All right, great job. Absolutely. So our answer is going to be C here, because this is our only categorical variable, and a bar graph is used to display categorical. That's probably not spelled right. Categorical variables. So since the rest of these are quantitative, height is quantitative, dollar amount is quantitative, and same with grades. If they're number grades. If these were grades in terms of like letter grades, that would be categorical, so like A, B, C, D. But if we're talking about just grades in general, like percentages, that's going to be quantitative. So since these all are quantitative, C is our only one that type of model car is going to be a categorical variable. So that's why that's our answer. So great job, guys. Okay. Okay, what is the mode of this pie chart? So go ahead, try to read this, and let me know what you think. All right, great job, guys. Absolutely. So thank you for your participation. You guys are doing a great job. So remember, our mode is going to be the most commonly occurring. I cannot write and talk at the same time. Numbers. So in this case, if you look through this, even though we're not giving the numbers, visually you can tell that Germany has the largest piece of the pie here. So UK's, in a close second. They're trying there, but Germany's winning here. So our mode is going to be Germany in this case. And if you were to actually see numbers here, this would be the largest number. So it's the most commonly occurring. Just like Brian said, it's the largest piece. So absolutely, that's correct. And you guys did a great job with that one. So good job. All right. All right. Okay, so a farmer is conducting a study concerning the heights of pigs on the farm. She takes a random sample of 50 research pigs, and measures each individual's height in centimeters. Which of the following is an appropriate graph to display this data? So I'm going to read through these and let me know what you think, and we'll go over it. Yay, good job, guys. Absolutely. You're thinking really well because remember, so if they're talking about height in centimeters, this is going to be a quantitative variable, but this is one quantitative variable. So a scatter plot, remember, is representing two categorical or quantitative variables, excuse me. So that can't be the correct answer because we're only talking about one. And then same with C and A are talking about we're talking about categorical variables, so those can't be the answer either. So D has to be the answer because it's our only graph that's talking about a one variable quantitative display in this case. So that's where we get that. So great job. Our answer is D there. All right. A kindergarten teacher wants to analyze the number of girls and boys in her class who like vanilla and chocolate ice cream. Which of the following is an appropriate graph for displaying this data? So similar question. See what you get out of this one. Absolutely. Great job, guys. So in this case, we have two categorical variables. So we have two of these. So it's going to be gender and then flavor of ice cream. And so since we have two, two-way table is the best because this is going to be talking about categorical variables. Scatter plot is talking about quantitative. So we wouldn't want that one. Same with the dot plot. This is also going to be quantitative. So that's why we don't want that one. And then a bar graph is categorical, but it's talking about one categorical variable. And we're looking for two. So that's why A can't be the answer. So C is our answer because this is talking about two categorical variables. So great job. Okay. All right, holding all other factors consistent, how does width of a confidence interval change as sample size decreases? So go ahead, read through these answers and let me know what you think. Yay, you guys are so speedy. You're doing a great job. Okay, absolutely. So remember, we do have an inverse relationship between sample size and the width of our confidence interval. So it's, in this case, our sample size is decreasing. So that means that we're going to have a wider confidence interval because the width is going to increase because this is inverse relationship. So one increases when the other decreases. So A is our answer because these ones just don't make sense. So awesome, good job. All right, I think we have two more. Okay. All right, a hypothesis test for a population proportion P is given below. And if we find that the p-value is 0.033, which of the following describes this data set and its conclusion completely with a significance level of 0.05? So let me know what you think about this one. You guys are doing so well, absolutely. So our answer is D here. So if we look at this, since our alternative hypothesis is not equal to, that's what's giving us this two-tailed part of it. And then it's for proportion because, see, we have our P here, so that's our population proportion. Remember, null and alternative are always written in terms of the population, mean or proportion. Here we have proportion because we have p. And then we are going to reject that null hypothesis because our p-value is less than our alpha, because 0.033 is less than 0.05. So we are going to reject that null hypothesis. So that's going to be in favor of our alternative hypothesis. So yeah, D is our answer here. So good job. Okay, one more. So which of the following symbols can be used when writing a null and alternative hypothesis? This is just to make sure we have a good grasp on what different types of symbols we can use. Oh my god. Okay, there we go. Try this one out. All right, absolutely. So yeah, if we remember, our null and alternative hypothesis are always written in terms of our population. So that's going to, out of these, A and B are our only ones that are population symbols. So that's why our answer would be E, because these are the two that are our population symbols. These are both going to be for samples. But remember, since our null and alternative are always written in terms of our population, we would write, so your null is always going to look like this. It's always going to be mu equals something, or if it's a proportion, it'll be p equals something. So remember, always an equal sign. And the alternative will be the same thing, except it won't contain an equal sign. It'll either contain not equals to, greater than, or less than, but it will always contain mu or p for means or proportions. All right, great job, guys. You did a really, really good job with this. Okay, so you can watch this one back, and since we kind of, only briefly went over everything, it's kind of just to make sure we hit on all the topics, and, if you went through and there was something you're kind of like, oh my gosh, I totally forgot that we did that, I definitely want to review that. Go ahead back to the other videos that we've done in the other group reviews to review those specific topics, in the description section of each video, we do have the a description of the different topics that we covered in that one, so you kind of know what you're looking for. If you guys have any questions, comment on the video, I can get back to you that way, or email me, whatever works best for you. Our next review for the same PowerPoint for the midterm will be on Thursday at our normal time for 10 p.m. That we usually do for our group reviews. If you haven't already given me your Penn State email into the chat box, please do that for me, just for attendance purposes, not to email you or anything. So if you have any questions now, you're more than welcome to type them into the chat box. If not, you guys are good to go for tonight.